Hello everybody and welcome to this video which is all about second derivatives. So we're going to have a discussion about second derivatives, what they mean, and we're going to do a an example to kind of illustrate what we can use these for. So let's recall that the first derivative, okay, of any function is literally just the slope at your choice of x, slope at any x value. Okay, that's what the first derivative is. And what the slope tells us, it tells us how fast the function in question is increasing or decreasing. So how fast f of x is changing. Whoa, little sneeze there. Sorry about that. Anyway, first derivative, how fast f of x is changing. So the second derivative, if I can type there, let me get rid of that. Boom, get rid of that. Second derivative is going to be the rate of change of the first derivative. Because that's what the derivative tells us. It always tells us the rate of change of whatever is in there. Rate of change of the first derivative, which is the slope. Rate of change of slope. Okay, how is the slope changing? Okay, so let's look at some simple examples to illustrate second derivative stuff. Okay, so if I have a simple thing like this, let's look at this little curve here. Okay, let's think about what's happening to the slope as we go across here. So as we start out here, the slope. Let me my keyboard's in an awkward spot here. Let me grab this and move it to a better spot where I can actually use it. 1 second. I'm so sorry, everybody. Thought I had everything set up the way it needed to be, and of course I do not. Okay. Anyway, here we go. So this thing starts out. The slope is extremely negative. Okay, and as we keep going from left to right, what is happening to the slope? Is the slope getting more negative? Is it getting more positive? Or is it staying the same? And as we can see, hopefully we can see, as we're going from left to right here, this slope is becoming more positive, okay? Here, super to the left, the slope is super negative, and then it starts to become less negative, and then right here we have a minimum, and at the minimum, the slope is going to be 0, and of course we talked about that in a previous video. And then as we keep going to the right here, the slope becomes just increasingly more positive, okay? So this is the embodiment of a positive second derivative, okay? So in your mind, if you ever see, something that telling you that the function's second derivative is positive, then this is what is occurring. And something like this is happening. Okay? Likewise, okay, if we look at the opposite situation, right? If we have a curve like this, yeah, we can ask the same question: what is happening to the slope as we go from left to right? And as we can see here, super to the left here, super to the left here, the slope is extremely positive. And then as we keep going left to right, here at the maximum, the slope is exactly going to be 0 there. And then as we keep going to the right, the slope here is negative. Okay, so in other words, here, the first derivative is decreasing. Okay, first derivative is decreasing. So what that means is that my second derivative is negative. Okay, and likewise up here, this tells us that the first derivative is increasing. In other words, slope is increasing, right? Slope is increasing. Okay, so this is what a second derivative means. Second derivative, a positive second derivative means our slope is increasing. Our slope is getting more positive. A negative second derivative means that our slope is decreasing, or our slope is getting more negative from left to right. And of course, if the second derivative is 0, well, that means that, as soon as I can scroll down here, let's look at that just for a second, right? Second derivative is 0. Let's take a look at this situation for just a second. Okay. Well, let's think, what functions have a second derivative of 0? Well, how about this? How about functions whose first derivative is a constant, right? If I take the derivative of any constant in the world, I'm going to get 0. So if the first derivative is a constant, then my second derivative is going to be 0. Well, what does that mean about f itself? Well, if the first derivative is constant, then that means that the function itself is going to be that constant multiplied by x. And just for the sake of this video, let's call that kx. Okay, and what type of function is this? Everybody, this is a linear. This is a linear function. Okay, so a linear function is a perfect example of something with a no second derivative, second derivative of 0, no curvature. Okay. And this curvature is literally just a change in slope. Curvature, like I said, is change in slope. Okay. All right. Now, there is some important vocabulary that I should have mentioned a minute ago, and I just got. Let's talk about some important vocabulary. This first example that we did here, as we can see, this guy, this little curve is opening up. Okay, I hope everybody can see that. And for that reason, we call this concave up. Okay, concave up. So concave up means second derivative is positive, and likewise, we call this concave down. Concave down for the same reason, right? Because the second derivative is negative, but it's opening down. This thing is opening down. We call it concave down. And your function is concave down anytime your second derivative is negative. Your function is concave up anytime your second derivative is positive. Now down here, no curvature. There's no concavity here. Okay. So good. So yeah, so awesome. So now let's take a quick look at what it looks like when we change from concave up to concave down. So let me make it just a curve like this. Here we're concave up, and now we're concave down. Okay. So what's happening here is from here, I'm gonna sketch in red here, right? Starting here, the slope is getting more positive, right? We start out with super negative slope. The slope is becoming more positive right here. The slope is 0. This is where our minimum is going to be. This is where the first derivative is 0. Now our first derivative is going to be getting more positive now. First derivative is positive, first derivative is positive, first derivative is positive, until we get about here, okay? This point is very, very important. This is called an inflection point. ladies and gentlemen. Okay, so inflection point. Inflection point is going to be where the second derivative changes from negative to positive, or vice versa. Okay. We also have an inflection point if our second derivative changes from positive to negative. Okay. So anytime we go from opening up to down or down to up, we call that an inflection point. Okay. And I want to highlight in a different color the concave down portion, right? So we're concave up until that red point, and then as I'm sketching here, the slope, what's happening to it? The slope is positive, but it is getting closer to zero. Getting closer to zero. Now the slope is exactly zero, and we reach a maximum. No, that should surprise nobody, right? And now, as we keep going, the slope is now negative. Slope is now negative. Slope is now negative. So in other words, as I go from left to right, from the inflection point, the slope is becoming more negative. Okay, so we start out pretty steep positive, and then we are just getting closer to zero and then negative. So we're getting more negative the whole way. So for the blue portion here, the second derivative is negative. And for the red portion, the second derivative is positive. Okay, so this is what an inflection point looks like. This is what it looks like when the second derivative changes from positive to negative. Yeah, awesome. Okay, so now, I think conceptually we've done pretty good here. Let me think if I've missed anything. I guess, yeah, one more thing, right? That is, I guess, maybe two things. Here, the second derivative is exactly zero. Okay. So that's how we find these inflection points. First, we find where the second derivative is zero, and then we show to the left of this point that the derivative is either positive or negative, and then to the right that it's the opposite. So in other words, if the second derivative was positive here, then it has to be negative here, or vice versa. And that's how we have an inflection point. And again, that's where the curvature changes from concave up to concave down. All right. Another thing, one last thing, and then we're going to wrap this video up, and then we'll do the example in another video. So right here, check this out. Look at this maximum, okay? Now, here's the maximum. Now, clearly, we know by now, if we're watching this video, we should know that the first derivative at this maximum has to be zero, okay? And we are used to the first derivative test where we show that the first derivative is positive here, and we show that the first derivative is negative here. That's the first derivative test. We can also do this, okay? In other words, show that the slope is zero here. And then, right? Then, because the second derivative is negative here, in other words, because the slope is decreasing here, if we just plug in the x value into the second derivative and show that it's positive, then this is another way to justify extrema. Okay, this is called the second derivative test. Okay, and likewise down here, look here, okay? Right here, the first derivative, the slope, is exactly zero, okay? And we can use the first derivative test. In other words, we can show that the slope is negative here and that the slope is positive here, or alternatively, we can make note of the fact that the second derivative is positive here. In other words, the slope is increasing in this region. Okay? So we can either do the first derivative thing or show here that the first derivative is 0 at this point, and plug that x value into the second derivative and show it's positive. And that gives us another justification for a minimum. Okay. So again, condition for a minimum for second derivatives here, condition for a maximum second derivatives here in yellow. Okay. So this gives us a max. All right. I'm gonna call it for this video.